Thank you for the introduction. Right, so as the title says, today we will look at a different application of mathematical programming than what we are used to in network calculus. So I'm giving a quick outline of the talk. I'll start with a quick motivation on what we used mathematical programming for in network calculus previously, what the general idea of this new application is, and which practical example we're using for the remainder of the talk. Then I'll present the rough modeling approach, followed by an example evaluation using this approach and a short conclusion. Right, so as we've seen at this Wonica and in previous published work, mathematical programming has proven to be very useful for network calculus, and especially for obtaining tight bounds in networks, especially when network calculus might not be able to actually provide these tight bounds. However, this is really most of the usage that we've seen. So we always just want to obtain numerical bounds for a given network. We know everything in this network, and this is it. And an additional point that we've also seen at Wonica already is that the scalability isn't great, but Stefan has already provided some insight into how we can change that issue. So just to give a brief overview of the previous work of mathematical programming and network calculus, we've seen quite early applications where we had networks with arbitrary multiplexing, where the usage of PMOO caused issues because it would not regard topological information and as a result would not provide tight bounds. However, we were able to get these with the usage of mathematical programming. Next, we've seen quite a few works that focused on modeling tandems and also feed-forward networks with arbitrary and FIFO service policies, which will also be the basis of the example that I'll present. We will just extend them a bit. And also another point towards the scalability, we've also seen an improvement of these previous approaches by relaxing the constraints of the mathematical programs to make numerical bounds for larger networks computationally feasible. Right, so all of these approaches had something in common, and that is we know that the service curve that we used in the mathematical program was correct. So we had a proof, and we knew the proof was correct and the service curve was correct. However, what happens if this is not the case anymore? So this means we have a conjecture on a service curve that we do not know yet if it is correct. This means it's not verified. It can have several reasons. For example, the proof turns out to be too difficult at the moment or needs more work. Or we might have one and it's wrong. For example, it's a new technique that we're using and we're not confident that it's correct. Now, the question is, how can we still make statements about this conjecture on the service curve? And the interesting thing is, even if we are not sure yet if the service curve is correct, we are still able to model it in an existing MP model by modeling the description of the service curve in the model. And the result of this MP can then serve as a basis of further research into the service curve. So if the results align with what we expected them to be, they can serve as more evidence towards the correctness of the conjecture. However, they will not replace the proof. They can also serve as a kind of sanity check for the service curve proof if the results as well align with what we expected. And as practical example, we will use or we'll look at IEEE TSN with asynchronous traffic shaping, in particular the interleaved regulator. We've seen quite a few talks on it already at this Wonica, so I'm not going to introduce it further. And the thing with the interleaved regulator is that the known service curve is a fixed delay. This means that if we use the concatenation theorem for network analysis, we don't really have the potential to improve the end-to-end delay bound, since each application of the interleaved regulator will just add a constant delay. And we have a suspicion for a different service curve. However, the proof turned out to be quite difficult so far because the interaction of aggregate scheduling and per flow shaping is quite intuitive when we are applying it in a formal environment. And another thing that we've also seen in the talks yesterday is that the interleaf regulator, if it's a minimal interleaf regulator, provides the shaping for free property. This means it does not increase the aggregate worst case delay. And as such, this application or this example turns out to be a perfect candidate for the MP comparison because we know what the optimal delay in the network has to be. Right, so we jump into the actual modeling approach. So if we have a network element, we have a service curve conjecture for it, we are able to characterize constraints that have to hold for this network element. So this can be, for example, the maximum or minimum output, can be shaping constraints or other properties that we need to model this element. In the best case, we have a concise description of the element or of the behavior of the element, and we can map this description to network calculus constraints. This is the case for the interleaf regulator. We have a concise description of the output and can use this description to get constraints. And if this is not the case, it should prove quite easy to still get a complete description of this element, since this approach is thought to be used when we are at the point of already searching for a service curve. So we should know the assumptions and the behavior of the element. Right, so for the description, I'll just give a brief overview of how to map the description to the constraints, so you get a better idea of what the general approach is. So we start with the description, and we know that the interleaf regulator transforms an input packet sequence into an output packet sequence, and the output for each packet n is defined as the maximum of either the arrival time of this packet, the departure time of the packet before this packet, or the earliest time that this packet adheres to the regulation constraint of its flow Fn. So how would we model this as NC constraints? So we assume that we have an IR, an interleaf regulator, it's a network element, and we assume quite a basic network. So we have a flow aggregate consisting of two arrival processes, A1 that belongs to flow F1 and A2 that belongs to flow F2. And those are constrained by arrival curves alpha1 and alpha2 respectively. We can then characterize the output of the IR by first a causality, so that for any time t, the arrivals have to be, the arrivals of flow I have to be larger than the departures, quite a basic assumption. Then we also need to preserve the existing FIFO ordering of packets within the aggregate. We're using the definition by Anja here. So just if we have two flows, F1 and F2, and we have 2 points in time t and u, if the departures of flow I at time t are larger than the arrivals of flow I at time u, it follows that the same has to hold for the other flow and vice versa. And as a third one, we also need to model the pi regulator, the pi operator. So we just say that the departures over the interval ranging from S to T are upper bounded for each flow by its arrival curve constraint. So once we know all constraints, we are able to integrate this description into an MP model. So what we need for this is some basic model that includes the usual NC constraints. As I've mentioned previously, we've used the model of Anja. So we need a service policy, we need arrivals, we need timing constraints, etc. Just the basic construct to model a network. Then we also need some sort of description of the output that replaces the service curve constraint. So we've seen this previously. And we need other constraints that are specific to the network element. So for example, shaping constraints or anything else that is specific to this network element. And again, at the point where we would apply this approach, this should all be known and quite easy to put into the MP model. Right, all that's left now is to solve this MP and to obtain worst case delay for the specified service curve. So here's the big caveat, I'd say, and it's if modeled correctly. So we always need to keep in mind that we are operating on service curves that we have not yet verified. So this is always a concern. So any results that we get here, we should take with a grain of salt. However, if we assume that it's modeled correctly, the result serves as an exact worst case delay for the network element. And once we have obtained this result, we need to interpret and compare it to our initial suspicion of the worst case delay. So it means the theoretical bound that we started with that we could obtain with the service curve before using any mathematical programming. And there's really two things that can happen here. Either the result is too optimistic or too pessimistic, which leads to the suggestion that either our MP is modeled incorrectly, or we have a mismatch of what we assume for the theoretical bound and what we have actually put into the MP. And the other case is that the result is identical or close to what we expected, which is a good sign. Right, so now we go to the example evaluation. So I'll just give a brief overview of the workflow and then go into detail on how this approach is actually applied when using it. Okay, so our network setup is we have two token bucket constrained flows, F1 and F2, and we have a server tandem consisting of n server pairs. In the example, we use 9, but it can be done for any amount. And we use the pair split that was previously used in literature, where we consider the rate latency service curve and the interleaved regulator at the next server as one pair. So you see it down here. It's basically this pair. And we also assume FIFO. Right, and the workflow, it's a bit irritating because it kind of is bottom up, but I'll just start from the top. So what we do is we model a basic MILP for a FIFO system consisting of n servers in a tandem. Then we transform the IR description that we had into a set of min plus NC constraints and model them in the MELP. Then we model another MELP with our suspected service curve. And then we interpret and compare the result of the MILPs. We compare those to first the theoretical NC bounds that we obtained using the service curve conjecture. And we also compare them to the state-of-the-art end-to-end delay bounds for the interleaved regulator. So we now start basically with how this approach comes to be. So when we first start this, we have a delay bound, end-to-end delay bound for our service curve conjecture, but this doesn't really say much. We have no idea if it's a good bound, it's a bad bound, if it's realistic or not. So we need to compare it against something else. So the first step or logical step is to compare it to bounds that we can find in literature. So we compare it to the additive bound that I've discussed previously, and we can see here that up to 3 servers, the additive bound is better, but then it starts being larger. So this poses an interesting question. Is our result correct, or we really can't tell if we are here on the right track or if just the service curve is completely wrong? So the next thing that we do is we model an MILP of using our service curve conjecture. So we get a comparison of what we get as a theoretical bound and what we get with the MILP. And as you can see in this example, it is exactly the same. So this means that at least we can figure our assumptions are sufficient, but we really aren't much smarter now. I mean, we know that the MILP with this service curve conjecture is the same, but what can we do otherwise? And here the shaping for free property comes into play. So we know that the optimal bound for a network using using the interleaved regulator should be exactly the same as if we wouldn't have interleaved regulators, at least on an aggregate level. So this means what we do now is we compare these results to an MILP using the IR description. As we know, it's a minimal interleaved regulator. And as we see, it is way below both curves. So it means for one server, it's identical to the additive bound, but then it just has a normal shape that you would expect. So with this information, we can now make more statements about our service curve conjecture. We know it's not too optimistic. So we have this covered. And we also know that the observation we made at the start is not concerning for us. So this is really the general idea here, that with this approach and with comparing it to known bounds that are correct, we can gather more evidence towards whether we are on the right track or not. Right, and now we come to the conclusion. So we've seen a novel application, quite different to how it's usually used, of mathematical programming in network calculus. At the point where we use this approach, it's easy to set up since we are already searching for a service curve proof, so we should have all the information. And it gives us additional assurance during a period of uncertainty before we have actually found the proof, to know if it is worth looking for it further. And again, the important note, this does not replace the formal proof. So this approach can only falsify our conjecture. It cannot prove it. And this was my talk. Thank you for your attention, and I'm ready to take any questions. Yes. 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 Oh, okay, so this was quite a dilemma because it's currently under, oh yeah, okay, the question was, what is the actual conjecture on the interleaved regulator service curve? And this was quite a bit of a discussion because the result is currently under review. So I've decided to not include it in the actual talk, to not run into any issues. I hope you understand that. Yes.
By this figure, the bottom curve that you computed was above the green. What could you compute?
Okay, so the question was, if the bottom plot was below what we was above the green line, what could we conclude? Okay, as I've mentioned previously, so if the result of the MILP with our service curve conjecture is too optimistic compared to what we know to be basically the lower bound on the delays, or the lower bound on the worst case delay, we would know that we have some error either in our modeling of the mathematical program or in our whole approach, meaning that we, for example, we missed an important assumption, or we just the service curves just cannot be correct. Okay. The question was if this service curve provides a lower bound rather than an upper bound. So we have to make a distinction here. So it is a lower bound in the sense that we cannot go lower than this bound when we are looking for another service curve, because we know if it is lower, it cannot be the worst case, because this is basically the the actual, what we know to be the minimal worst case bound. So if
depends on the conjecture you're not showing, right?
Yeah.
That's why we couldn't interpret that. But it must, depending on this conjecture, we don't know yet. This line must be lower, and so this confirms in the sense of not falsifying this conjecture.
Yes. So that's really the general idea. I know it's a bit difficult, and I was a bit conflicted on whether I should include it or not. But yeah, so really the idea is that we know, since we have the shaping for free property, we know what the optimal delay bound should be. So if our conjecture would produce a lower delay bound, we would know it cannot be true. So that's why it has to be above. Yes, please.
If it works on one example, I mean, if you have a wrong service square conjecture, you will notice that in the first example that you apply this, or that depends also on the network and the example that you apply.
Yeah, so the question was, just because we have found one example where this is the case, how can we know that it is correct for arbitrary networks? Yeah, so currently this approach is, well, the conjecture is quite limited since we can only use tandems with two flows. So what I've done is I've basically written quite a lot of different cases, like edge cases, like how does this behave with a large difference in rates of the flows, with different utilization levels, different burst relations, etc. So really the idea is that you have to conduct a lot of experiments with different parameters to really get an idea if this is always the case or if you were just lucky to find one. So yeah, this is basically the idea. So it is in a sense quite similar to simulations where you really have to do a lot of them to really see what the general tendency is. Exactly. Yeah, that's like the big thing that you want to try.
Time for one last question.
Okay, thank you.
Yes.
Can you show slide 11 again?
Yes. Oh, yes.
So here the property of the interleaved regulator that we know assumes that S1 is FIFO globally. And you're looking for a service curve property of the block interleaved regulator. So in some sense, this property cannot be just local to the block, because if I change the block S1 by, for example, a WRR node, the delay bound that we know for IR probably does not work. Probably very bad things will happen. So in some sense, the service curve, which cannot just be a property of the interleaved regulator alone.
Okay, so the question is, we currently assume that S1 is a token, is a rate latency service curve. But what happens if we replace this block, for example, by a WRR block? How does this behave to the interleaved regulator service curve? That's the gist of it, right?
That's not really my point.
Oh, okay.
S1 could well be rate latency, but not globally FIFO.
Okay, right. So the question is, what if we don't have the global FIFO assumption? Is probably more like it. So okay, this goes kind of into conjecture. So we have assumed both cases. So there was quite a lot of debate whether we can actually find a service curve only for the interleaved regulator, or if we always have to consider the server that comes before it exactly due to this. So do we have to consider what happens at the server before, or can we actually find a kind of independent service curve? And so the general idea is that we consider the input to the interleaved regulator and what can really happen there. So either How does the burstiness increase look like from the server before? What happens if the flow arrives first that is not bursty? What happens if the flow arrives first that, or packets of the flow arrive first that are bursty? And basically, we have different assumptions that in the end all led to one unified service curve that would work for all different assumptions of what we actually get as input to the interleaf regulator. So in this way, we avoided the issue of assuming what actually happens at the server before. So we do not assume what happens before. We don't assume the order of the flows. We just really assume what arrives at the interleaf regulator.
I think we're now all very, very interested in your conjectures. We wish you all the best for its acceptance, and please announce it on the network calculus mailing list so we all get a notification.
I will.
See that conjecture. So let's let the speaker